I was thinking about this just a few minutes ago, and scarily, it's around about 5 years since I actually worked on Carrapateena, and that's how quickly time flies. It's 18 months since I last said anything publicly about Carrapateena, so I've got my cheat sheet, I hope you don't mind. And so, yeah, as Ken said, we're doing a bit of a tag team here, and what I'm going to talk about today is I'm going to talk about the discovery history of Carrapateena and then talk about Tech's involvement, the geophysics that we did while Tech was owner of the project, and then Charles will go on to talk about the Oz mineral time. And I apologise, there will be some things here that people will have seen before because for fairly obvious reasons, given that I don't work for Oz or Tech now, I could really only put out what I had already sort of put out somewhere, what was already published somewhere. So I'm going to talk about the location very briefly and the discovery history in a bit more detail, touch on the geological setting, and then I'll go through the geophysical surveys, well, a summary at least of the geophysical surveys that were undertaken while Tech was working on Carrapateena, and then draw some conclusions on their results. So the Carrapateena iron-oxide copper-gold deposit is located about 160 kilometres north of Port Augusta and 100 kilometres southeast of Olympic Dam in South Australia. The project area lies on the Panatti Station pastoral lease. It's located within the Andamooka Ranges, where we have gently to moderately sloped hills that are extensively covered by quartz sandstone. Vegetation in the area, pretty sparse as you can see, mainly saltbush, bluebush and shrubby eucalypts. And I have to admit, while I was working out there, it was a mystery to me how the sheep survived, but somehow they did. So since the discovery of the giant Olympic Dam deposit in 1975, the Gawler Craton has been extensively explored for IOCGs. In the late 1970s and early 1980s, Carrapateena Exploration Company, along with its joint venture partners, were drilling drilling holes on gravity and/or aeromagnetic highs, and in particular they were drilling an area called Salt Creek, which is about 100 kilometres southeast of Olympic Dam. When it came to looking at the different prospects on the Carrapateena leases outside of the Carrapateena deposit, I had the opportunity to name them, and anybody who's been there knows that Carrapateena is absolutely the windiest place on the planet. So all the prospects that we named were actually named after different winds around the world, and Salt Creek is now known as Carmson. Oops, I have to get that pointer right, just here. Back in the Carrapateena exploration time, they drilled a hole SASC4 and completed the hole to 1,250 metres depth. They intersected hematite sericite altered Donington Sweet from 520 metres to the end of the hole, and this provided encouragement for later explorers such as Tech and Oz Minerals to look around the Carmson area. RMG Services Proprietary Limited is a South Australian unlisted company that was incorporated in 1974. Its principal is Rodolfo Gomez, who previously studied mechanical engineering and extractive metallurgy. So RMGS actually first applied for an exploration licence for an area on the Torrens Lake, southeast of Carrapateena. And the reason for doing that was because Rudy Gomez wanted to get a source of salt for a petrochemical plant at Port Bonethon. After extensive searches in the Purser Library, Mr Gomez's interest in the Gawler Craton for IOCG deposits was fuelled by these, and he started thinking that perhaps the Carrapateena Arm and the Torrens Hin Zone might actually make the area prospective for IOCGs, because apparently it wasn't so great for salt. So in the early days, we had the regional aeromagnetic and gravity data that was collected by Purser, and in that data there was an Olympic Dam style, I've got to stop doing that, style signature here. So we have the gravity anomaly here associated with Carrapateena, and that's on the margin of this broad magnetic domain shown in red. Now the gravity anomaly is, I guess, fairly subtle, being 2 to 2.5 milligauss, and just over here is the Salt Creek or Carmson anomaly as well. Now, following looking at the actual gravity and aeromagnetic data acquired by PERSA, RMGS, in a joint venture with General Gold Resources Limited, repeated the gravity survey at greater detail and confirmed the presence of both the Carrapateena and the Carmarthen anomalies. In 2003 to 2004, there was a joint venture between MIM Exploration Proprietary Limited, Terramin Australia Limited and RMGS, and through that joint venture they undertook further gravity surveying. MIM also completed 5 kilometre long lines of IP resistivity and MT data using the proprietary MIMDAS system. So at the top here we have the gravity image and the 6 lines of MIMDAS data that were collected. This line in particular is 738-100 east and basically goes over the top of the Carrapateena deposit. What I've got shown here is just a rough location of where the hematite breccia plus or minus sulphides are. So with these data, MIM basically modelled a conductivity structure indicating that there was at least 150 metres of conductive overburden having a conductivity between 0.05 and 0.1 Siemens per metre, and this was overlying a several 100 metre thick layer of resistivity where the material was greater than 150 ohm metres, and then you had the underlying basement where there are variable but significantly lower resistivities, and in particular this conductivity anomaly here was interpreted to be coincident with or slightly north of the gravity anomaly that the survey was going over here. And the Carrapateena, let's move on. Carrapateena is located within the G2 tectonic lineament that was interpreted by Tim O'Driscoll back in the days when he was working on Olympic Dam. So the project benefited quite a bit from structural studies, and these were actually undertaken by Dr. Rodney Boucher, who had studied with Tim O'Driscoll and understood the methodologies that Tim had used. The project also benefited a lot from Chris Anderson, who was working as a consultant to RMGS, and Chris played an integral role in the discovery of Carrapateena because he was involved in the modelling and interpretation of the data and the siting of the drill holes that led to the discovery. So in February 2005, RMGS actually applied to PERSA under the PACE funding to drill 4 holes at Carrapateena. This program was actually revised to 2 holes and was approved and half funded by PERSA. So of these 2 holes, first hole here, Car 1, was actually targeted on the conductivity anomaly, and Car 2 was targeted on the gravity anomaly. So the image I have here is actually Bouguer gravity image, but the yellow outline here just shows where the residual gravity was. Now Car 1 unfortunately actually drilled down a dike, so there were hundreds of metres of not very interesting rocks there, but Car 2 was the discovery hole. And there's a very happy looking Rudy Gomez following the discovery. So Car 2, we've got 178 metres at 1.83% copper and 0.64 grams per tonne gold, including 75 metres at 2.89% copper and 0.4 gram per tonne gold, and that's obviously a little bit of drill core from Car 2 that Rudy's looking at in that photo, or pretending to look at. Probably. So, following the discovery, Teck were in there like a shot. So, it was only a couple of months later, Teck started farming in September 2005, and after extensive exploration by Teck, we finally improved on the discovery hole with Car 50 and 905 metres at 2.1% copper and a gram per tonne gold. In addition to the extensive drilling that was carried out on Carrapateena, we also had the opportunity, in fact it was a commitment, to drill on the regional prospects, and the results of this included identifying hematitic breccias at Carmarthen and copper mineralised chlorite, sericite and hematite altered granites and breccias at Fremantle Doctor. In April 2011, Oz Minerals purchased Carrapateena and subsequently released an inferred resource of 292 million tonnes at 1.29% copper and 0.4 grams per tonne of gold, and also 207 ppm of uranium and 5.4 grams per tonne of silver. And as many people would have seen from the recent announcements this year, that further drilling at Carrapateena and Fremantle Doctor has also identified significant copper mineralisation there with really quite good grades. So as I said, Carrapateena is located here. This G2 lineament that was interpreted by Tim O'Driscoll. So we're on the eastern margin of the Gawler Craton in what's known as the Olympic ASEG province. So the Gawler Craton is a region of Archean to Mesoproterozoic crystalline basement that underlies most of South Australia and has not undergone substantial deformation in the past 1,450 million years. The Mesoproterozoic eastern margin is bounded by the Torrens Hinge Zone and covered by younger Proterozoic Stuart Shelf sediments and local Paleozoic cover. So Carrapateena, as mentioned, is located at the intersection of major north-northeast and northwest trending structures, and these are analogous to the ones that are thought to have played a key role in focusing the mineralisation of Olympic Dam. So here I've got a schematic geological section and just resistivities annotated for the different rock types. So Carrapateena lies under approximately 470 metres of moderately conductive Stuart Shelf sediments, and these present significant challenges to exploration there. The cover sequence comprises the Wilpena group overlying the Umbaratana group sediments. And the Wilpena group consists of this Arcoona quartzite, Corabera sandstone and Wimmera shale, and the Umbaratana sediments, basically the Snuckalina Formation, the Rainella siltstone and the Angiopaina Formation. So this lies unconformably on the basement, and this unconformity here is marked by a basal conglomerate that's sort of the order of metres to tens of metres thick. The actual mineralisation is hosted within the Carrapateena breccia complex, and it occurs in a hematite, chlorite, sericite mineralised sequence of partly conglomeratic sediments with clasts and fragments of granite, gneiss and vein quartz. So these sediments are likely derived from hydrothermal activity resedimenting a brecciated host. The host rock is a variably foliated and or sheared gneissic quartz granite and quartz diorite, which has been age dated at 1857 plus or minus 6 million years, which assigns it to the Donington Suite. And the base rocks are locally intruded by felsic and mafic dikes. So just a couple of drill core samples here, and I've got a few little abbreviations. So hematite, sericite and chlorite, the abbreviations I'm using here. The alteration minerals consist of hematite, chlorite, sericite and locally abundant quartz and carbonate, being siderite and or anchorite. The secondary minerals comprise barite, monazite, anatase, magnetite, apatite, fluorite and zircon. 3 types of hematite are observed, so a fine-grained earthy red hematite, a massive steely grey hematite and a platy specular hematite. The copper sulphides are dominantly chalcopyrite and bornite, and these mainly occur as disseminations, blebs or veinlets, and there is rare chalcocite in the deposit. Pyrite's locally abundant. In terms of the physical properties, there were 72 samples that measurements were made on. The cover sequences basically exhibit low densities, magnetic susceptibilities, chargeabilities and EM conductivities. They have high apparent porosities, variable P-wave velocities, and with the exception of the Arcoona quartzite, which is highly resistive, the cover sequences are weakly to moderately conductive and show significant electrical anisotropy. In the basement rocks, the densities tend to increase with increasing hematite and or sulphide content. The magnetic susceptibilities are directly related to the percentage of magnetite. The EM conductivities are generally low, but there are rare localised exceptions. And the lower galvanic resistivities and the enhanced chargeabilities in the basement are directly related to mostly the iron oxides, but also the presence of sulphides. And the responses are generally, as a whole, the physical properties are really dominated by the iron oxides, and the iron sulphides and copper sulphides are a lesser component or a lesser influence. So in 2005, Fugro Airborne Surveys flew an aeromagnetic survey on behalf of TEC. The data that were collected were magnetic and radiometric data on a 200-metre line spacing in an east-west direction, and the mean flying height was 50 metres. So Carrapateena, this This is an image of the first vertical derivative of the aeromagnetic data, and Carrapateena really is this blip here on the southwestern margin of this moderate magnetic domain. The anomaly at Carrapateena itself is only about 20 nanoteslas. So outside of the PERSA data, there have been 3 detailed gravity surveys undertaken at Carrapateena. The General Goals survey that I mentioned earlier was done on a 500 metre by 500 metre grid. Then in 2003, MIM collected data on a 400 metre by 400 metre grid, and in 2006, TEC collected data on a 200 metre by 200 metre grid. So the image I have here is just an image of Bouguer gravity, and I'm showing the breccia outline, the hematite breccia outline here in grey, the chalcopyrite in yellow and bornite in blue, so just the surface projection of those. And as I mentioned before, the actual anomaly associated with Carrapateena is really no more than about 2.5 milligauss. So Jim Hannison from Adelaide Mining Geophysics undertook some forward modelling of Carrapateena using his proprietary software. Jim, in recent years, has been using this phase diagram when looking at ASEG deposits, and basically it's plotting density versus magnetic susceptibility. And for the Gawler hematite-dominated ASEG deposits, simplistically, pink is good because you're looking then at rocks that are basically dense and not very magnetic. So in his modelling, he has simplistically modelled Carrapateena as being this sort of vertical cylinder having a diameter of around about 1 kilometre, and that being quite dense but not particularly magnetic, overlying this deeper column, of which of course we've got no resolution on the bottom, and that's more magnetic, or magnetic and dense basically. So he'd used a density here of 3.27 grams per cc, and this more magnetic body down here would correspond to a body that would only have really a couple of % of magnetite. Now, Jim could equally model these data with something completely uninteresting like a mafic, and of course that does have some implications for exploration that, you know, and highlights really the issue of ambiguity here. Luckily for us, that, you know, and for everybody involved in this project, this model was actually closer to the mark than the uneconomic mafic. The other thing that Jim did at the time was he simulated the situation where if you reduce the cover over Carrapateena from 470 metres to 350 metres, just like the situation with Olympic Dam, what would the Carrapateena response look like? And through that modelling, he basically estimated that if you did that, then Carrapateena would produce a gravity anomaly of only about 3.5 milligauss and a magnetic anomaly of perhaps around 30 nanoteslas. So really, despite that 120 metres extra of cover, it didn't really make a lot of difference in terms of the gravity and magnetic response of Carrapateena, and possibly not as much difference as people would think. So I had some inversion modelling done as well. This was done by Craig Beasley from Wave Geophysics in the US. And what I've got here, I've got isosurfaces of density contrast are shown as the pink and grey, and isosurfaces of percent magnetite shown in the blues and greens. And the model was actually constrained, the gravity model was actually constrained basically for the cover. So it incorporated an overburden layer of about 450 metres thick with a density contrast of minus 0.1 grams per cc overlying a half space. We found that if we didn't constrain it for the cover like this, we'd end up with dense sources within the cover, which, from what we know of the cover rocks, wouldn't have been geologically realistic. If you think back to the model before I showed you from Jim Hannison, and then this model here, and basically showing that the dense body, or the near coincidence, I should say, of the gravity and the magnetic responses as opposed to being completely coincident. At the time that we were working in TEC, we had drilling down to greater than 1,500 metres, and that basically confirmed that in the shallower section you would see mostly hematite, and it wasn't really until getting down to quite great depths around 900 or 1,000 metres that we were starting to see very small amounts of magnetite coming in. So in 2006, Search Exploration carried out a 2D high-powered IP resistivity survey using their proprietary technology. The data were collected on 7 east-west lines that were 300 to 400 metres apart, with readings being taken at 100-metre intervals. The line lengths varied between 3.9 and 5.1 kilometres, with a total of 40.7 line kilometres of data being collected. The maximum transmit current into that survey was 68 amps. So hold that thought when I talk about one of the later surveys. Overall, the data quality was quite good, but the data almost invariably showed an increase in chargeability with increasing N level. And this was due to the significant amount of EM coupling at larger N spacings. Some data were also negatively impacted on by the tellurics, and as best they could, these were actually minimised through sophisticated processing undertaken by both David McGuinness from Montana Geophysics and John Payne from Scientific Computing and Applications. And this slide here just shows a little bit of the search setup in terms of having the little auger rig to put in the electrodes, the remote control on the transmitter, and then the full time series data coming through on the computer. So the image up the top here is just the Bugay gravity, and this shows the location of the 6 IP lines over there, and the line I'm going to talk about is actually this line here, 6543800, which is actually about 300 metres north of the Discovery Hole Car2. So the inversion model that's shown here was done with the 2D Zong software, and we have the apparent resistivity pseudo section here, and then the resistivity model down here, and I've annotated onto it an approximate location for the hematite, breccia and the sulphides. So this, on the resistivity side of things, seemed to have worked reasonably well. We have an anomaly here, and it's modelled as a conductive body here that seems to roughly correspond with the location of our deposit. So that's good. And when we get to the chargeability, things are a bit more complicated. If you look in the inversion model, there's a chargeability high here, but if you look in the chargeability pseudo section, it's a little bit less obvious, I would say. So the chargeability data, unfortunately, were quite ambiguous and very, very highly variable from line to line in terms of what we thought we could see. In fact, we spent endless hours in tech arguing about what we could and couldn't see in the data. And I guess the conclusion that we came to is that whether or not we could actually get a chargeability response from the deposit seemed to be tied in a bit with whether the hematite and sulphide mineralisation was actually in contact with that unconformity or whether it was sitting down deeper. Also undertook a MIMDAS survey, and this was a 3D ghost line survey. So we actually had 3 grids here, grid north, grid middle and grid south. And by having these 3 grids, we also collected 7 lines of collinear IP resistivity and MT data. Each line was about 4 kilometres long and around about 400 metres apart, with a receiver dipole length of 200 metres. The transmitter locations were extended to the east and west of the survey area by 500 metres. And sorry, I should have mentioned that that's back on the gravity image again that I'm showing that. So in terms of the MT data quality, this is just an example of a reading of the MT data. And as you can see that we actually got quite clean data with good data right down to about 0.1 hertz there. Now with the IP data, generally they were of good quality, but what we did see was that the dipole pole data seemed to be dominated by a lot more negative EM coupling below n equals 10 when compared with the pole dipole data. So when we did the subsequent modelling, we decided just to use the pole dipole data. We weren't entirely sure about the reason for this, but it could have been tied in actually with the conductivity associated with Lake Torrens to the eastern side of the survey. So in comparing Search's high-powered IP results with the MIMDAS results, this first diagram on the left here basically shows a resistivity profile from the MINDAS survey, and then these yellow isosurfaces are conductivity isosurfaces from the Search High Powered IP survey, and I think there's a pretty good correlation there between the two. And on the right-hand side, we have the same MIMDAS resistivity profile and the isosurfaces from the gravity model, so the isosurfaces of density contrast, and again, pretty good correlation between the conductivity anomaly from the MIMDAS and the gravity body there from the model. So fairly happy with the resistivity part of the survey, but I guess the ambiguity that we were seeing and the different results from the chargeability gave us less confidence that we were actually seeing through the cover properly in all places. So I was more inclined to rely on the MT and resistivity data than the chargeability. Also tried some downhole IP with mixed results. Tried 3 different ways of doing it and for different purposes. So we had in situ measurements in 21 drill holes, and these were using a collinear Wenner array with about a 3 metre electrode spacing. Also attempted radial IP measurements, and this was done in 6 drill holes, and we had a transmitter electrode located at the bottom of the hole, one located at the hole collar, and then one located at 1.5 kilometres away from the hole. And the potential electrodes were laid out in this radial array where we had 8 lines and 5 electrodes, basically 100 metres, with 100 metre spacing in between them. And unfortunately, those surveys weren't so successful and very difficult to work with the different polarities and make sure all the polarities were correct, and very difficult to interpret the results, and possibly not really the appropriate survey to be doing with that thickness of cover and the sort of conductivities we were dealing with. We also tried cross-hole dipole surveys, so we had a 100 metre transmitter in one hole and 50 metre receiver in the other, and again mixed results. It wasn't clear if we were getting a successful survey there or not, and probably was scope to actually reprocess the data and have another go at it. So but just having a quick look at the in situ IP resistivity, this is the discovery hole, CAR2, and got the resistivity profile shown in red and the average IP profile shown in blue, and I've annotated here just very broad lithologies there, and as you can see, basically we are getting increasing chargeability and decreasing resistivity where we would hope to see it in the hematite breccia plus or minus sulfides. And while we were throwing everything at it, we also did some EM. We did downhole EM surveys, 3-component downhole EM surveys in 4 drill holes, and also a single surface moving loop profile. The data were collected using the 42-channel Crone pulse EM systems. The survey was carried out by Outer Rim. And for the downhole surveys, we used the 600 metre by 600 metre transmitter loop. For the surface surveys, we were using a 200 metre by 200 metre moving loop in-loop configuration with a transmit current of about 30 amps. And this is basically the surface profile, and again I've annotated where the hematite breccia and sulfide should have been sitting, but really we couldn't see any convincing evidence of that at all. And similarly within the drill holes, while we could see very small local in-hole responses, we couldn't see any evidence of any type of off-hole response. So not surprisingly, EM really wasn't the tool to be using here. So in conclusion, Carrapateena is associated with a weak discrete ellipsoidal magnetic response and near coincident weak bullseye gravity high. It's also characterised by distinct conductivity anomaly. It should of course have a chargeability anomaly associated with it, but the chargeability data were somewhat ambiguous. The EM surveys did not provide any responses that could be attributable to bedrock conductors, and I personally don't recommend them for the Olympic Dam style ASEG deposits. Geophysical responses are really dominated by the presence of iron oxides, with the sulfides playing a lesser part. So I'd just like to acknowledge Rudy Gomez and his associates for the discovery of Carrapateena, the tech geoscientists and my colleagues and other some very talented consultants who were working with me on it. and also Oz Minerals for their subsequent work. It's really been amazing what they've done there, and it's just wonderful to see the drilling that they're doing and the results they're getting, and I appreciate their permission to talk about it one more time. And thank you very much for listening. Also, I have some references there for later on when this presentation becomes available to everybody, and thank you very much.
Thanks, Lisa. That's good. Died of thirst. We're getting there. All right. You weren't first.
Yeah, thank you very much, Lisa. That was a terrific talk. And I just wanted to make the comment that this discovery was and is an example of opportunities won and opportunities lost. And when we talk about exploration undercover, we're often thinking about the greenfields exploration undercover, but as you very clearly pointed out, this is an area where people have walked over for decades before. But in reference to the opportunities won and lost, first of all, the opportunity won for Rudy Gomez and the Government of South Australia that partnered in the drilling of those discovery holes, and then the opportunity won by Teck and then subsequently by Oz. I've got to say I still feel very sad for Mount Isa Mines. MIM were lining up to drill this. This was a top priority hole to be drilled on this target in 2004, and that was exactly at the time that Xstrata took over Mount Isa Mines. And of course, at the time of the negotiation of the takeover, all drilling was stopped. So one wonders what would happen to this deposit. Would it have been discovered if Mount Isa Mines had drilled and not hit it? No, you know, as in the first hole.
Nick was named the various deposits after beers rather than...
Yeah, great job, Leslie.
I don't know so much how history might have looked if MIM had it, but I think in a lot of ways it has been a complete win-win all around. It was great for Rudy and his associates. It was wonderful for Teck, and when Teck sold it, they made a tidy profit that they were very happy with. I think it's been wonderful, it is wonderful, and it will be wonderful for Oz. So I think it's just win-win all the way at the moment. It's just great.
Thanks, Lisa. The downhole IP showed that it should have been able to be picked up with an IP survey. Do you think that was due to the depth of cover or the orientation of the ore body being a steeply pipe-like body?
To be honest, I can't. It's so far back now, so I can't even really picture that data. You're talking about the radial, I assume.
No, the surface IP.
Oh, sorry, the surface IP. Sorry. No, I think it was. I think it was more related to the cover conditions, I guess.
With that IP, Lisa, how did the chargeability of the Mindas survey compare with the search stuff?
This is where it became quite complicated, because obviously I was, comparing back and forth and modelling and remodelling and getting 20 different opinions and so some lines actually compared quite well and sort of compared with what we knew of them geologically, and then you'd have other lines where the MIMDAS seemed to look a bit better, and then other lines where the search looked a bit better, and it was just inconclusive, basically.
Just speaking of cover conditions, on a couple of the resistivity profiles, there seemed to be a bit of a break in the conductive cover right above the deposit. Is there any significance in that?
That is true, and the actual mineralisation, at the very least, is structurally controlled there, and I guess, to be honest, it's a little hard to get a good handle on structures when I guess you've got the small pierce points of the drill holes and but very little regionally to go by. So it was almost like being too far but being too close as well. So we were starting to get a handle on structures in terms of where we were finding the highest grade mineralisation, but it took us a long time to do that. That's why I sort of said what I did about the Car 50. For a long time we were just going blindly. We couldn't seem to vector it properly. It wasn't you can be in the middle of that system and you just can't see the forest for the trees, basically. So yes, it may have been tied in with those structures, though.
I'm going to actually, in my question, answer one of those previous questions.
Great.
With the first IP survey, your maximum receiver transmission distance, receiver to transmitter distance, would have been about 1,600 metres, n equals 8 at 200 metre dipoles. The maximum penetration you're going to get realistically in good conditions is about a third of that, which is about 500 metres. So essentially, even if the conditions had been good, chances are the IP wouldn't have seen it simply because the spread wasn't big enough.
I should say, just as a comment, we did actually experiment with 300 and 400 metres at the time and made the decision to go with the 200 metres because that seemed to... we were running across the line, across the discovery hole. We were just constantly using that line.
You still would have had trouble because with the dipole-dipole arrangement, the EM coupling is always positive. So you're never going to be able to tell the difference between EM coupling and a target anyway. But with the MIMDAS survey, you had the pole-dipole-dipole-pole combination, and what you saw there was the EM coupling, which was negative in one direction and positive in the other. Instead of throwing away the negative values, you can actually use that geometry to correct for the EM coupling. And it would almost be interesting to go back to that data now and see if you can actually correct that coupling geometrically and see if there is actually an IP anomaly there.
I had a question. With the physical property logging, the downhole chargeability logging, did you load that up into one of your geophysical block models and generate the forward solution for the chargeability to see what that might have shown? I assume you did, but I didn't see a picture of it.
No, we didn't. And one thing that probably won't be any surprise to you at all was that the numbers that we would get in the lab measurements and the numbers we got downhole were actually quite different. So the contrasts were the same, but the numbers, the actual amplitudes were very different. And I guess, you know, and this was sort of a bit of discussion too with Don Emerson about this. Neither of them were, you couldn't say that one was more reliable than the other for different reasons, basically. So we were choosing not to trust the numbers at all for either of them.
Such is life. Okay.
Still on the chargeability, the very last section you showed had because you're saying there's not much chargeable response, it had a pretty subtle but kind of maybe not to be disregarded anomaly. I don't know, looked about 100 meters depth or something. Did that have anything to do with this system and like a water table or a paleo water table or something like that?
There is around 100 meters, yes, there is.
What is that feature?
So there is a water table. I think it was about 90 or 100 meters. I don't know if Charles, if you... Sorry, don't worry if you weren't listening. but somewhere around that depth there was.
So do you know what that subtle chargeability? I mean, is that something that kind of would stay in various inversions? Is that a robust feature that could have been associated with the mineral system, even though it wasn't the actual mineralization itself?
To be honest, I just couldn't say now. Yeah.
Chris, I can answer that. There's some real disseminated sulphides in some of the covers.
Just getting back to your experiments down hole, and I've been burnt pretty bad trying that sort of thing myself, and the IP turned out not to be of any value at all. But I was just wondering how you went with the apparent resistivity calculations. Did you, with your dipole in one hole and dipoles in the others, did you get anything useful out of that?
Yeah, it did look interesting. And it did look like it could have been useful. I should say there's a small context in all of this too. When we got to a certain point in the exploration, like when we had drilled a certain number of holes, we actually had to down tools irrespective of where we were in terms of finalising geophysics and things like that. It was just part of the I guess the deal side of it all. So we never really got to the point that we wanted to get to with that downhole. And it was John Payne who'd been working on it and trying to sort that out, and he sort of had a suggestion of what he thought was going on there, and maybe it wasn't, but we down tools at that point, so just never really got. So it was left, unfortunately, not closed off properly.
Okay, I think we'll close it off there. Thanks again very much, Lisa.